Ja dann, hallo und herzlich willkommen.
Well, hello and welcome. I am delighted to be here today. My name is Alexander Meier, and I work for Symeo, a senior principal embedded software engineer. And here I look at functional safe sensors. And if you know Symeo, and as you can see on the screen, we deal with radar sensors. And the SPS format is new to me, so I'm very happy that I can be here and participate. And my colleagues who shared information with you were very interesting, and I looked to that, and there was one I found, one statement I really liked. So they said radar is magic. It's magic. And as an engineer, I say, oh, well, why is a technical piece of equipment magic? I thought about it, and well, it depends on what you look at. If you look at it from integrator or customer side, it might seem like magic because radar works. It works in good and in very bad environmental conditions, and this is why it often is considered as that. And the high availability that the system is there and is always around is a very essential property if we talk about such a system. And this takes me to my presentation. I would like to show you a concept for a safe positioning of a radar in rough environments. And for that, I came up with a presentation in 3 segments. First, I would like to look at the rough environment and where you find it. Why is it the case that they make it difficult for sensors to work? And based on that information, I would briefly like to explain radar technology to you. And following that, I would like to look at why radar can work so well in rough conditions. And based on that, I would like to show you our LPR SAFE system, which is a 1D measurement for distances. So rough environments, what is it? You might see it behind me. So this is what we encounter quite frequently, rain. So rough environments are often considered to be outdoor applications. So rain is everywhere. You saw it this morning. Well, in this season, you just need to be calculating that rain might happen. And optical systems have a problem with that. Why? Because optical sensors need to have a clean space so that we have a good resolution, that a signal can be emitted and a raindrop can really harm. And on the other hand, we need to measure. And if we have laser sensors that are disturbed by rain, then your measured values start to vary, and that is very difficult if you have a very delicate application. And then we have fog. Fog is something we know as well. If we're traveling by car and you come into some fog and there is very little light, and camera-based systems are hitting their limits quite easily in that. Ultrasound, well, it looks very robust to start with, but we need to know how the sound travels, and that correlates with fog, and that can reduce the performance. So it's important to know, and I want to open your eyes. I'm not only talking about the outdoor conditions. It can also be rough conditions in a process. If you have a process where hot material needs to be cooled, during the cooling, a lot of fog can be generated, or moisture in the air. And what we often have in processes as well is dust. In the steel industry, for example, heavy industry, dust is a problem for optical systems, but not only optical systems. You could also think about what else you have. For example, instrumental encoders. They also work mechanical, so you need to clean them mechanically. And if they're hermetically enclosed, then you don't have to clean them. The combination of different environment conditions could be a problem. Just think of an industry that is very dusty, and you have dust in combination with moisture, with humidity, could form lumps. And there is mechanical slip, and the signals are not correct anymore. So this could be a KO criterion for safety relevant processes. And last but not least, we have factors like stray light. If you have light that interferes, if there's too much sun is shining into the camera, so external light or process-related light, light arcs that form and UV light, all these are effects that lead to a environment that for a lot of sensor technology is very demanding, and to have a functional system can be difficult. So the question is, why radar? And here I briefly would like to explain the way how a radar system works. And what we can see here is on your left side, on my right side, there is a radar sensor. A radar sensor emits an electromagnetic wave, and to be precise, an FMCV signal, so a frequency modulated wave. And where do we move, in what range? And I visualized the spectrum for you. You can see the radar technology ranges between 20 megahertz, and it says 120, but currently it is 240 gigahertz. So we're covering a very wide bandwidth. But we are moving in the ISM band. So industrial, it's between 24 up to 240 gigahertz. And if you calculate that or break it down to the wavelength we're using, you can find out that this is millimeter wave sensors. And this wavelength in the millimeter field is one of the properties that is relevant for a robust system. So you can say that as long as stray particles are smaller or are minimal compared to the wavelength, then they don't interfere with our signal. So a radar sensor can, depending on the depth of the particle cloud or the number of particles that are in its way, can cope with that. So on the right, you can see we have frequency of up to 300 terahertz in wavelength that's micro or nanometer size. And that leads to a range that particles in the air could cause problems. So the industrial radar on the right side is in a spectrum that offers robustness, but because of the high frequency, a very good local resolution of a few millimeters. So you need to trade off. So if you reduce the frequency a little bit, there are less interferences in the megahertz range, but then the results will be less good. Now, if you have a magnetic wave that's sent out from the radar, the performance depends on three things. One part will always be absorbed. So that's not available anymore. The second component we encounter is the transmission. So radar waves have the property that the targets, depending on the material, can be permeated. And this is a property we can also use when we design a system. On the table on the left, you see the transmission ability of different materials. You can see metal cannot be permeated. So very little is going through the metal, but a lot of the wave remains on the surface. And plastic, paper, or cardboard also have the same property. So if you have a very difficult to see radar target, is really not detected well, if you add a piece of wood, then you see it much better. And you can also use it to build a robust system. And a radar doesn't have any mobile parts, so no micro mirrors. We're static. We're working with antenna arrays. And because of this transmission, we can set up a system. The antenna you can see here, and the electronics that are built in can be protected well. So it's a robust system also regarding the environmental conditions. And the last part we see, the last part of this wave movement is the reflection. You can see that is a primary radar. So you're actively sending a magnetic wave that hits a target, and then the reflected part is what comes back to the radar. And why do you need to know this? Well, the reflected performance is described by the radar equation. I don't want to go into too much detail here, but these components show you what the critical elements are. The reflected performance is what we need for the detection. So as much as we send out, we will get something back. So PR is PT, and then you have a calculation with which you can scale it. So these are the antenna definitions, and you can see the wavelength plays a role here. The longer the wavelength, the higher the performance of the laser. But it is a trade-off with the exactness. And then we have the radar cross-section. The radar cross-section describes how well our target can reflect electromagnetic waves. So that depends on the property of the material of the target. But the radar has an opening angle as well. So the further away the target is, the more remote it is, the further the window opens up and distributes across the entire surface. And you can see that is why we have r to the power of 2, and you need to calculate it this way. So the path to the target and the reflection are both to be considered and calculated. So the more distance you have, the less performance you have. And what is the good thing about the primary radar and the measurement? Our measurement principle offers us two ways of measuring we can use. On the one hand, we have the time of flight measurement. So the signal duration is calculated to the distance or to the target. And the second thing is the Doppler effect you can use. So the frequency shift of the received signals can be calculated. So how fast is the target moving? And we always work with a passive reflection. And the further away the target is, the larger my opening window is, and the more difficult it is to hit my target. If there are other hurdles on the way, you can detect those first, possibly. And that, with a view to functional safety, is a no-go, because you don't know what you're measuring and what your reference is. And based on this fact, we have a secondary radar principle. So the secondary radar is replacing the target by a second radar unit. So you now have a master and slave approach. They're pointing to each other. The master sends out a signal, and this signal only needs to be detected by the slave. So the cross-section, or something like the distance doesn't really play such a big role anymore because the slave actively absorbs the signal and sends it back. Now, if you look at the properties that are relevant for a safety system, we have this comparison. You can see the measuring principle of a secondary radar is a passive one, and we have an active reflection in the other system. So the scalability is inverse with r to the power of 4, the distance measured, and the secondary radar has r to the power of 2. And with the secondary radar system, you can reach much further targets, up to 1 kilometer of measuring distance. And another very important point is the uniqueness of a target, the unambiguity. So the opening angle of the radar becomes wider with distance. And sometimes you don't really know which target you're measuring. And this problem can be addressed by us by using the secondary radar, which actively responds. And this active answer allows us to know exactly, do I still see my partner or not? And last but not least, the radar cross-section is of essential importance in the secondary radar model. Now, you know the two technologies, and I would like to show you the concept how our LPR SAFE system for safe distance measurements. The 1D distance measurement is comprised of 4 elements. And these are pairs, so a secondary radar concept, and the data of the system is plausible because of the secure PLC. So the PLC calculates whether the data is reliable. So we have 2 secondary measurements that we compare to each other, and then the plausibility is calculated. So what are the benefits? The inherent technology of the LPR SAFE system are, as I already mentioned, with the unambiguity of the target. If we want to be sure, we really need to know where we're measuring. So if we have a distance measurement without a reference, we don't have any benefits. That's not a safe system. And because of this active answer between master and slave, we have the closed current principle. So we can look at the timing of the devices which we know, and we can see whether the system performs as expected or not. So this is the closed current principle. We have the possibility of checking the measurement for its plausibility before we send it elsewhere. So it's validated and can pre-filter or evaluate it before we're sending it. And last but not least, because of the closed current principle, we have the possibility of detecting the absorption or loss of data. If we have a primary laser that tells you, I don't see anything, you don't know whether the radar technology is not working, whether there's anything sent out, is everything absorbed, or are we just measuring into empty space? And the secondary radar gives us this possibility of responding to all this. We have a great robustness, and that's essential for the availability of the safety function and for plausibility checked by the PLC. So we're first checking for plausibility in each radar distance, the measurement data, and then the metadata that's made available, and that with a temporal component. And these 2 parameters give us a great possibility of making data safe. And last but not least, we have several channels. And these several channels can be characterized by a logic per channel and increase the safety further. And the system also can be degraded. What does it mean? Thinking of the retrofit aspect, we have a secondary distance. And if we add the LPR SAFE system, and this system has an error, then we at least have one measurement distance, and you can fall back to the normal operation level we had before. So if we are processing hard steel that should not be in the open air for a long time, I can control it with an operator into a safe state, as we did before. So based on this concept, we can offer products to the market in very little time in the near future, with a distance to up to 300 meters, up to 300 measuring exactness or accuracy of plus minus 10 millimeters, and a measuring rate of 50 hertz and 20 hertz in the other case for the LPR 1D24. If you'd like to see the radars in action, we're in Hall 7A. 406 is our booth, and we have a demonstrator there for you. And I would like to thank you very much for your attention, and am available for questions in the Meet the Speaker corner. Thank you very much.